Okay, this question here is about a space vehicle that re-enters the Earth's atmosphere at an angle theta to the horizontal. Now, because of the resistance, the space vehicle uh, doesn't accelerate, it travels at constant speed, and then there's below the space vehicle, usually there's some heat shield. The heat shield actually dissipates heat at a rate p so that the temperature of the vehicle remains constant. Okay, so you're asked to express the rate of dissipation of heat P in terms of mg, v, and so on. So let's draw a simple diagram. This is our atmosphere, the vehicle. I said vehicle, I draw as a single mass that enters at an angle. Okay, angle here from the horizontal. This horizontal is theta, so this angle is theta. So supposing the velocity here is v. Okay, so what happens is now is normally there's a decrease when you drop this, when the vehicle drops from a certain height to a lower height, there's a decrease in gravitational potential energy. So loss in gravitational potential energy is normally given by gain in Ke plus the gain in this case gain uh, in heat energy, okay, or in thermal energy. Okay, maybe I should call it thermal energy. Gain in thermal energy. Okay, so what happens now is there is no gain in K because it's traveling at constant speed. So the loss in GPE will be therefore given by gain in thermal energy. All right. Now, so in principle, the temperature, because of the gain in thermal energy, the vehicle would therefore um, become hotter and hotter. There'll be a rise in temperature. We are told that uh, the the mean temperature, you can see that the mean temperature remains constant, means that even though the vehicle gains thermal energy, but it is able to dissipate heat at the same rate. So whatever it gain, it gives away. Whatever it gain, it gives away. So there is no net gain in thermal energy. So the net dissipation is the same as net gain. So that there's no net gain, not net increase in temperature. So this gain in thermal energy actually is the same as heat thermal energy dissipated. It means the heat energy given out to the environment, to the air atmosphere itself. So whatever thermal energy they gain from the friction is actually given back again to the atmosphere. So if you our loss in GPE actually is therefore equivalent to the heat dissipated. So you divide both sides by time, it will give you the rate, right? If we divide by the change in short interval time, that represents a rate of, so that I can write down as a rate of loss. Okay, rate of loss in GPE will be the same as rate of dissipation. Okay, rate of which in this case is our P. Okay, rate of heat dissipation. Rate of dissipation of heat. Okay, and this is our P. This is the one given in the question above. Dissipates heat at the rate of P. Okay, so on the right hand side we have P here. So on the left hand side is the rate of heat loss of rate of loss in GPE. So we know that this vehicle dropped down from at an angle here. So let's say in a time t here, it travels a distance along this direction here. This x equal to v times delta t. This is the time that it travels along that angle. So along this vertical direction, it will be v delta t times sine theta. Okay, so along the decrease in height, the decrease in height is actually v delta t sine theta. Okay, the decrease in the distance along the diagonal direction is v delta theta. So the vertical decrease in height is v delta theta sine theta. So the rate of loss in GP therefore is actually mg times the height v delta theta sine theta and divide by delta t. Okay, so as you can see, the time and time can cancel away. So therefore, P can be expressed as mgv sine theta. Okay, so next the answer for this question here. Uh, this rate of heat loss is actually very high. It can be so high that it can actually disintegrate a spacecraft. There was an accident in the space shuttle on re-entry. Actually, the space shuttle disintegrated and burned up because some heat was allowed uh, uh, to enter the sub part of the wing, and because of that, the entire space shuttle was lost.